Ah. Ooh. Uh. 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 Hello. 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 Ah. Look at my mic's being. Bitch. God damn it. Ah. Everything's ruined. Man. Man, the mic's not good. It's lying to me. It's lying to me. Man. What? Whoa. Man. Shave that bush. You can't tell me what to do. What the f wrong with the mic? You can't tell me what to do. What the mic? Crazy. I don't even know if you can. Push the stand. Right here. Okay. On the list of this, not the bush. The bush is what gives me. I swear, I had like I've been. You don't know why. Oh, bro, you don't even. Bro, I'm better. I'm better than the why. What the fuck is wrong with this mic? Dude, I spent so long, and then like the second before I hit, I see that my mic is gone on OBS. OBS, the mic has disappeared from the screen. I don't, I don't understand. And now it's being a bitch. It's being it's never been. What the fuck? Is it the order of the filters? Holy shit! It might. Oh my god! It's the order of the filters. I'm a gad. I'm a gyat. I got him. Okay. Everything is good now. Hopefully. I'd be wiser than Socrates, bro. Bro, you don't even know. You think Socrates has got anything on my level of wisdom? You'd be fucking wrong. Oh, you'd be so wrong. My ass is at least like 20 Socrates, bro. Is what you need to understand, my disciples. So you need to understand, my disciples, that I am, in fact, one of the wisest of our time. Our time being 200 BC or 200 BCE if you go that way. Ah, today's a special stream. Today's a special deliberation. I tell you. I tell you, my wise disciples, today is special. I hope you brought your cuneiforms, your stone tablets, and I hope you're ready to learn. Because today we be learning. I'm just waiting for. Actually, I should probably check if the chat's gonna work. I should have probably checked that YouTube chat works on this. Yo, YouTube chat, you here? I'm gonna do my own test to see. It's probably not gonna work at all. Yep. it's about what I. It's about what I thought would happen. Uh, well, good thing. Good thing it's early on. I could test this out. there's no good way to test it out beforehand. Oh wait, did that work? I just saw something. Oh shit, it does work. All right, never mind. We're good. We're good. It works. Although it is very small, I should probably make that way bigger. Where is the chat? Make that bigger. All right, now we're cooking. Now we're cooking with the good looking, which is me. I am the good looking. My hands are cold, but my spirit is high. Spirit is hot as hell. Okay. And now I'm gonna do that going live thing that I do. Do a bit of this. All right. And now I'm ready to cook. Now I'm ready to cook. Okay. So now, my disciples, I know, I know. You may not believe it, but I believe that I know it's common knowledge nowadays. Okay, that the sun revolves around the earth. All right, the earth. We all know that Earth is at the center of the universe. Okay, okay. Just the gods would have wanted us to be in the middle. It makes sense. We get to look up at the cosmos and we see everything else surround us. Okay, why would we not be in the middle? You know, it just wouldn't make sense for the gods to place us anywhere else. You know, so that's what I've also thought for most of my life. But you know, I think I've come to a startling realization, and I think at the end of today, my disciples, you too will realize that not everything is as it seems. Okay, in fact, I believe it is very possible that the sun may be what's at the center and that we are revolving around it. Now, before we all start a war over this question, all right, I want to go over some things, okay? Today I'll be going over my hypothesis and why I think it could be proven that in fact heliocentrism is the reality of our universe. I know, I know. They'll get all your panties in a twist here. Disciples, you know, I came across a friend the other day. I know that's the most unbelievable part, more unbelievable than the heliocentrism idea. I know, but I came across a friend, okay, and he was showing me some things, okay, here in 200 BC. Now, his name was Aristarchus of Samos. I was passing by Samos, the city of Samos, because I had a colleague there who I'm not gonna lie, we're just gonna get drunk. That was it. We were just gonna get high and wasted and I don't know, like do some blow. Who cares? That's not what we're here. That's not what we're here about. I was there and I came across a fella, Aristarchus of Samos, and you know he had some compelling arguments. He had some compelling ideas, and I really like to share with them with you here today. Okay. Now the goal of today apart from the heliocentrism, is to simply observe the celestial bodies, make some conclusions, make some calculations, and see if we can determine what the size and the distances of the sun, moon, and earth are. Now, the earth. The earth is simple, at least for the distance. It's the simplest one. We know what the distance is. 0, because we live here. But the rest, I think you'll find, are a lot more intriguing to figure out. So, why don't we get started? I think. Are there any questions? Any questions about what it is we are doing here today, or why I have a beard, or why my name is Onwa? Now, I am a philosopher after all. It's only fair. Ah, my disciples. Today is going to be a very momentous day. We'll be learning a lot. A lot, I say. So, why don't we simply get started? And you'll see later tonight. Actually, I should probably say this before we get started. Later tonight, there will be a phenomenon which is going to be very important to the beginnings of today and what we are speaking about. For tonight, you see, is in fact a quarter moon. Now, there will be other things happening, obviously. The stars never rest for any man. There will also be the happenings of a meteor shower. And I think it'll be quite beautiful to see, or maybe be a little treat for us tonight. But tonight, on the land of Discord, if I find you there, we'll be observing the stars while speaking to each other. And perhaps we can make the same observations that I'll be making here today. So if you have some time tonight, please come on by to the Discord. But for now, let us start by making some observations. Okay? And for that, we must go to night. For you see, at night, my disciples, there is a quarter moon happening. Now, by itself, that doesn't sound like much. A quarter moon? Yeah, a quarter moon happens every so often. And you also might be asking yourself, why is the quarter moon look like more like half than a quarter moon? We'll get to that. We'll get to all of it. But a quarter moon is very important for what we're going to be doing here today. And I'll explain that right now. So, first, let's explain why a quarter moon is important. All right? Now, a quarter moon is important. Now, let me quickly draw you a very bad circle on my cuneiform tablet, of course. Now, a quarter moon means that half of the moon has been illuminated. Yeah. So, this actually, just by itself, we can make a very, very important observation. Now, what do you think this means if half the moon has been darkened and the other half is visible from the Earth's standpoint, right? From where we're standing looking up, what has this been illuminated by? Well, obviously, it must have been illuminated by the sun. So let's draw a sun right over here. Now, this might be, it's a bit, this is not to scale, obviously. The sun is much further away, as we know. But it is illuminated by the sun. And we here, the Earth, right? This is us. This is the observer. We're seeing that it is being illuminated half. And here it's being illuminated fully. From the sun's perspective, it's illuminating it fully. And from the Earth's perspective, it's illuminating it half. What does this mean? Are there any guesses? Any guesses as to what this can mean? I'll give you a second. You may not realize it. But this means something pretty interesting. Now, what this means, in fact, is that from the moon's perspective, if we draw a line from the moon to the Earth, and then a line from the moon to the sun, the angle between these two must be a 90-degree angle. Now that's very interesting. Very, very interesting. Okay? Because if we were now to make a line from the Earth to the sun to just complete this and make a triangle, this would mean that we would now have a right-angled triangle. Now, this, in of itself, might not mean much. But this means that we could find things like, we could use certain formulas like Pythagoras' theorem on this triangle. We can use trigonometry on this triangle. All right? So if we could just find the angle from the moon to the sun, from the Earth's perspective, right? If we're able to find this out, what is this angle? Then we could obviously find out what this angle is, right? Because we have the other two, and the triangle angles add up to 180. So we could find this out. This one's going to be easier because we're on the Earth, right? We don't have any information from the sun. Whoa, whoa, whoa. But if we could find these angles out, that means that we could then use those to figure out what the ratios are from the different sides. And once we know the ratios, we could utilize those in a very interesting way. So, now, the question is, how do we find this angle? That is the question. How can we find what this angle is? Well, really, it's the most obvious way. How else would you find this angle? Also, I will add a simple lettering so that we know what celestial bodies we were speaking about. The sun, the earth, and the moon. I don't know why I said it in that orientation. That's a strange orientation to say it in. But really, it's kind of the simplest way if we want to find the angle. Let us take a second and look at the moon. Now, I actually did this observation myself. Here's a picture of the actual moon. This happened October 29th, so last month. The moon was at a quarter moon. Now, I'm going to sneeze. You'll have to give me a second. I'm expelling the demons. You'll have to excuse me. The wisdom that I'm showing is scaring off the demons. So, once you have that, you could then simply look at the sun, take a measurement, make a line segment, look at the moon, make a line segment, and then you'll get an angle. Now, this might be a bit hard to see for those of the Thebes plan. Because of the horizontal, it's a bit hard to see with all the lines. But you can see I've drawn two lines there. Now, the angle between these two are very high. Very, very high. And you can use this to find out what the angle is. You simply have to make an observation, make an analysis of what that line segment is. You'll find it is approximately 1/30th of a quadrant. 1/30th. Let me write it down here. 1/30th of a quadrant. What is a quadrant? Well, if you remember the line, remember line segments, right? We have the x plane and the y plane. 1/4 of these is a quadrant. So this is a quadrant. This is a quadrant. Oh wait, you can't even see it. I'm sorry. Cameraman, can you please pan it back to the actual people that we're supposed to be seeing stuff? Right. Of course. My bad. Let me rewrite this. So 1/30th of a quadrant is what this is. This is the large angle. I'll redraw this to better represent the triangle later. But a quadrant is, if you remember this where you have the line, this is the XY plane where this is X, this is Y, right? Then these four intersections, these four individual points, these are all quadrants. So what we're basically saying is it's 1/30th of this. So like a line pointing straight up, that would be a quadrant, but this is like 1/30th. So it's like very, very small. Very, very small. So now I could draw a triangle on a new cuneiform. Let me get a new cuneiform out, new stone tablet. Now, if we were to draw this at the correct angle, it would be, if I were to talk about this in angles, in fact, it would be around 87 degrees. And then if we were to put this along with our triangle, if we were to try and complete the triangle here, do something like this, as you can tell, a very steep angle. A very steep angle indeed. But this would go out to be around, if I can complete the triangle first. there. Here we have our triangle, and we know that this is a right angle. This here would be around 87 degrees, or in other words, 1/30th of a quadrant. Now, does everyone? Oh, hello, hello, Rachel. Welcome, 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 my new disciple. Would you like? Would you like to be quickly caught up on what you have missed? We are talking about the sun, the moon, and the earth. Or you see, if you look at the moon at a quarter moon, you will find that the moon is at a right angle between the earth and the sun, because the sun, for the sun to illuminate it, so only half of it is seen at the earth, it must mean that it's at a right angle. And now we could take a look at the angle between the moon and the sun from the earth and find that is approximately 87 degrees. And that's what we're discussing now. Thank you for joining us. The goal here today is to figure out what the distances and the sizes of these celestial bodies are. And this is our first step to doing that. We are now finding the relative distances of these two. Where's the relative distance from the moon to the earth and the sun to the earth? That's what we want to know. And then from that, if we could get one measurement, we could get the other. Very simple. Now we have this. We have determined it is 87 degrees. Now we could simply complete the triangle here, saying that this is 3 degrees, because 87 plus 3 will equal 90. Then we already have the 90 here, so 90 plus 90, 180. There you go. That is what it is. Every triangle will add up to 180 degrees in total. At least every right triangle. I'm not sure about the others. I'm not gonna lie, I'm not the biggest math guy. I don't know all the math, so I'm not gonna lie to you when I say this. So now we could use this here, the angle. Now we know that here, this is the distance from. I'll put a D here. This is the distance from the moon to the earth, right? I'll put some circles here to remind us why we're doing this. So this is the moon, this is the earth, this is the sun, right? So now what we want to know is how many D's do we need? How many moon to the earth lengths is the earth to the sun? That is the question we now want to answer. It's a very important question. Very important question, my disciples. And luckily, with modern mathematics and modern trigonometry, we can use sin cos tan to find this out. Now, if you simply use cos, right? Use cos. This is the adjacent over the hypotenuse, right? That's what we'll get. We'll get the adjacent over the hypotenuse. which is d over something else. We'll get d over the xd. That's what we're getting, right? So what this turns out to be is approximately 1 over 20, around 0.05, 1 over 20. If you want my disciples, you can check this for yourself. You can make all these observations yourself. Again, we'll be doing them on the disc of Ord tonight to any disciples who want to drop by. Do some extracurricular. So, now what this means, if you remember, it was d over x of d. If this is 1, if d is equal to 1, then this will be equal to 20, which means our ratio is simply that. It's simply, let's remove, let's first remove the text. Whoa, what did I do? I think my wisdom was being seen by the Celestials, and they were impressed. I was doing some mathematics beyond the gods' comprehension. Okay, so this means if m to e, right, the distance from the moon to the Earth is d, then the distance from the sun to the Earth will be around 20 moon lengths, 20 distances, 20 moon to Earth distances. Okay? It's 20 times as much. Beautiful. So now we know this, and it's a great thing to know. And from this, we now have something very important. A very important piece of information. We know the sun must be very, very far away from the Earth. Okay. Next. We're not done yet. This was the first part in a very, very long proof. Now, I will show you something interesting. I will show you something very interesting. But first, my disciples, go get some rest. Come back to me in the morning. Welcome, my disciples, to the morning. Today, we're going to continue off from yesterday. I have come with some new information for you all. So let's get a new cuneiform tablet. I hope you've all brought your cuneiform tablet. Good, good. So, now, let's make an observation. Does anyone here, or has anyone here, I suppose, ever seen a solar eclipse? Does anyone not know what a solar eclipse is? All right. So, the reason I bring this up is because let's draw another diagram here. So, from the Earth, right? A solar eclipse happens because the moon covers the sun. Now, if if I were to create the sun here, and then create the moon here, this is very interesting. I tell you, my disciples, this is a very interesting fact. In fact, it's a very interesting cosmic coincidence that this is able to happen at all. Do you notice something? Do you notice what that coincidence is? And why it's so stunning? If you're all following the teachings of Euclid and using Euclid's geometry of similar triangles, you'll notice that the fact that this can happen, a solar eclipse just in of itself can occur, means that these are similar triangles. Now, similar triangles are very interesting because with similar triangles, if I know, for instance, that at this, for this, let's say this triangle, that I have this is equal to 1, this is equal to 2, this is equal to 3, right? Just just imagine this is true, okay? If I were to make this bigger, this triangle bigger, I just make a bigger triangle. That's it. It has the same angle, the same exact angle. But this length is now equal to 2, right? It's a triangle that's twice as large. Because I know that these are the same angle, I could simply say, well, if this is double, this, then this must also be double. And this must as well be double. And it'll be true. This will be true. Now, why is this important? Well, here is the reason this is important. From a solar eclipse, we can make the deduction that because this here is D. Remember this line segment here is D. And then this right here is the radius of the moon. Let's say it's Rm, the radius of the moon. Now, since we know this right here, this is ds, right? The distance to the sun. It involves dm. Remember, this here is 20 times d. This is the distance to the sun. Distance to the sun. I'll put a ds, and I'll put an m here just so we don't confuse ourselves. Then this must mean, because of the law of similar triangles, this must mean the radius of the sun is also 20 times the radius of the moon. This is very, very interesting. If solar eclipses couldn't happen, which again they shouldn't, it's very, very interesting that it does. We know that the sun must be 20 times bigger than the moon, and it must be 20 times further away. Amazing. But we are not finished yet. Okay? at least with solar eclipses. There's one more thing that we would like to do, and that is to create our own mini solar eclipse. Now, why would that be? Well, we know these facts here. The distance to the moon, distance to the sun, radius of the moon, radius of the sun. But what we need to be able to even utilize these is we need to know what these are, right? We need to know what these are in terms of the Earth, right? Because the Earth we can measure. We are here on the Earth, right? It might take maybe it might take forever. Maybe we have to walk all around the Earth to figure out what the length is, what the circumference is, what the radius is. But we can do it. But the moon and the sun, we can't go there. I can't walk to the moon. I can't measure the moon's distance, right? But if I can figure out in terms of the Earth how far away it is, or in terms of the Earth how large it is, well, that's trivial, right? That's something that I can do. So, for this, we can do something similar. We can create our own solar eclipse, my disciples. We can make our own solar eclipse. Now, this is going to be a very fun experiment. It's a very simple experiment, but it allows us to learn a lot. And that's something we love. We love learning. We love learning here. So, to create our own mini solar eclipse, all we have to do is take something of a known size and then measure how far away we have to be from it to cover up the moon or the sun. Now, this is something that our fella Archimedes of Syracuse did. Greatest mathematician of our time, I must say, here in 200 BC. I'm a huge fan. I'm sure you're all huge fans. So, what we could do, we take this diagram, right? And I'll use a coin. Yeah, I'll take a dime, right? The larger, you have to know that also, the larger you make your circular item to use, the further away from it you'll have to be. So I'll take coin. Here's a coin. Measure it. Now the measurement seems to be around 0.7 inches. Okay. And now I'll do something the world has never seen before. I'll do something that you might not have ever thought to do. I will now tape it to my window. Now you want to tape it to your window. Okay. So take a coin, measure it, tape it to your window, then get a measurement stick and see how far away do you have to be for that little thing to fully cover the moon. You could also do this in the day if you want. You could do this with the sun. I don't recommend it. That's what Archimedes did. I don't know why. Kind of stupid for that. But each their own. You do that, and then you'll get the measurement. The measurement here is around 90. So around 90 inches. Now what this means, if we try and get the 0.7 to a 1, it'll go to around 1 over 125. That's what our ratio is. Okay? Remember, this is the ratio for the radius to the distance. Okay? Well, actually, it's the diameter, not the ratio, not the radius. It's the diameter. Okay? So remember, this is the diameter, and then this is the distance. I'll just put a D. This is the distance. Okay? What does this mean? What does this mean? Well, it means that for all of these, because we made a similar triangle from this, right? This was the idea of making our own mini solar eclipse using the actual moon. Although you remember, you could use the sun. It means that the diameter of the moon, right? The length of the moon, okay, and the distance to the moon has this ratio. So the moon is 125 moon lengths from the Earth. So it takes 125 moon lengths to reach the moon from the Earth. And similarly, it takes 125 sun lengths to reach the sun from the Earth. Very intriguing. Very intriguing indeed. So now we know a bit more. But you might be saying, but OnwaVT, the greatest philosopher of our time, come on. You said we needed this in terms of the Earth. I did. And we will get there. We will. So why don't we go on, get a new cuneiform tablet, right? Keep it all in your head. We're getting closer. Next, we'll be discussing a lunar eclipse. But very quickly, why don't we simply go over, why don't we re-go over all the things, right? Let us learn. Let's go back and learn. So what have we done? What have we done so far? We've done a lot. First off, a quarter moon. Quarter moon being very important to the start of this. It's what started everything, really. Now, at a quarter moon, a moon is half lit up. Exactly half of it is lit up. Well, not always exactly half, but it's basically half. Hello, Tsumi. Welcome, my disciple. Welcome, my disciple. I'm so glad you came at just the right time. We're going over everything we have learned so far. So glad you could come. So, at a quarter moon, the moon is exactly halfway lit up. Let me show you the moon again. As you can see here, this is during quarter moon of last month, October 29th. As you can see here, the moon is half lit up. Okay? What this must mean, if you look at our diagram, the sun, from its perspective, is lighting up the moon fully. From our perspective, it is lighting up half of it. What this must mean is that at this point, the moon, at this point, the moon is at a right angle between the sun and the earth. The moon itself, if you were standing on the moon and you were looking at the earth, all you would have to do to see the sun is turn exactly to your left 90 degrees. Just turn to your left fully, as if you were in like a 2-bit, like as if you were in like a 2D world. Look to your left, like completely over, like at your shoulder. That's where you'll see the sun, 90 degrees. Okay. So using this, we can make a triangle, make a right angle triangle, right? If we just draw lines from the moon to the earth, the sun to the earth, and then the moon to the sun, you'll have a right angle triangle. Now, if we find the angles here, we could use geometric analysis to figure out it is approximately 87 degrees, which means the triangle would be like something like this. All right. It would be something like this, 87 degrees, if we use some geometric proofs and Euclid, if we use Euclid geometry. Right. Then we could use trigonometry to figure out that the moon to the earth, let's say it's distance, it's just distance, right? D, like we put D to denote it. Then we could use cos to figure out what relative distance it would be from the sun to the earth, right? So what we found is the moon to the earth, the sun to the earth is 20 times the moon to the earth distance, okay? And we can just find that with simple trigonometry, right? We have that. Now, we know this. So the sun to the earth is 20 times the length of the moon to the earth. Something extra that we should also know is because of solar eclipses, okay, when the moon covers the sun, if we draw the diagram, the only way this would be possible is if they created similar triangles. And what that means, what we can find from that, right, is that if the distance of the moon to the earth is 20 times the sun, if the sun to the earth is 20 times the moon's distance from the moon to the earth, then the length of the moon, right, must also have the same ratio, meaning the sun is 20 times larger than the moon. Okay? All right? This makes sense? Then we can take a coin, right? You don't have to take a coin, you can take a tube, or you could take uh you could take anything circular, really. tape it to your window, and then walk back and see at what point will you or will that coin or whatever else you got fully cover the moon. For me, it was around 90 inches. So 0.7 inches is the diameter of the coin, and then 90 inches was the distance, which means let's if I change it here to 1 over 125, this means the diameter being 1 would be 125 distances away. Now this is also a similar triangle. We could use the same idea we used here. What this means is that the moon is 125 moon lengths away from the Earth. Similarly, the sun is 125 sun lengths away from the Earth. If we want, we could. I'll just quickly. We won't use this, but I could quickly show you what this means in terms of all. If we just change everything to the moon, just change everything to the moon, right? So let's say we have the diameter of the moon. I'll make this big D. Diameter of the moon is just this, right? Now, the distance to the moon is 125 diameter of the moon. Okay, the sun is 20 times larger, 20 times further away. Sorry, so times 20, which means the distance of the sun is 2,500 distances of the moon, the diameter of the moon, sorry. And the diameter of the sun for now would simply be 20 times. So diameter of the sun is 20 times the diameter of the moon. Now we have everything in terms of the diameter of the moon. That's what I'm trying to get at here. This is pretty intriguing. But once again, we'll have to figure out what that diameter is, right? If we can't figure out what the diameter is, or the distance is, or anything, there's no point, right? We can figure it out. But are there any questions? I did go through a lot, and I'm not sure I explained it in the best way I could have. So if there are any questions, feel free to ask them. I will be drinking some water. On Twitch Varia's side, there will be ads in 3 minutes. So that's why I'm giving you guys a second for that. And then also, I'll wait for the ads to go. I'll probably see if I can get breakfast. Probably not, because I don't think there's anything I could eat without having to cook. I don't have time to cook in 3 minutes. So it'll be a bit of a break, I guess. But if my disciples have any questions, then you are free to ask them. Very free to ask. I'll go everything. I'll go over everything as many times as you may please. Crack, crack, crack. But if there's no questions, that's all right. We'll still be having a bit of a break while we await. And that is a-okay. Part of me thinks that maybe I should do more of these kind of things at night. Part of me has thought like maybe I should start streaming at night. I don't know. I don't know. For now I'm fine. As they say, chilling. That is what I do. Oof. As are starting in a minute. Oh Lord. Oh Lord. Oh Lord. Mhm. Mhm, mhm, mhm. Okay. Alright. Next, though, after the ad, on Twitch various side, we'll be talking about the lunar eclipse next. So stay tuned for that. Stay tuned, stay tuned, stay tuned. Stay tuned, stay tuned, stay tuned. Stay tuned la nuit. The ads are starting. They're starting. I'm gonna go find something to eat. Yeah, take a break. Take a break, my disciples. We'll be right back. Sorry. Ah, there's still some ads on Twitch various sides, so we shall continue to wait. I find this very intriguing. There's a lot more that I wish I could have spent time learning. I'll not lie to you. Aristarchus is very interesting, but it seems that if I wanted to learn more, I would have to possibly get a job at a museum and learn ancient Greek. And I didn't have the time for that. So it is what it is. It is what it has to be. As for like the trigonometry and such, I would have loved to learn the Euclidean geometry that he had done, but the internet did not have the answers, sadly. It simply said that he got it between 18 and 20. So, yeah. Welcome back, disciples of Twitchvaria. So, before we got into the Cursed Ad War, you see, I had spoken about lunar eclipses. Yes. So, why don't we get started on that? Get your cuneiform. Oh, it's out. Now, you might know what a solar eclipse is, but some of you might not know what a lunar eclipse is. A lunar eclipse is when the moon gets hidden behind the umbra of the earth. That might make zero sense. So, let us draw a diagram. So, once again, I'll take out one of these sorts of things, right? Here's the sun. I won't have space for it. Here is the sun. Here is the earth. And here is the moon. Now, what this triangle means is here is a shadow of the earth from the sun. The moon, sometimes, very rarely, not as rare as a solar eclipse, but very rarely, will be caught in this shadow. And you'll see it. You'll see this. If you look into the sky on a lunar eclipse, the moon will be there, and then it will go in and slowly disappear before showing up again. Now, this is actually pretty important stuff. Because with this, in a way, we can actually capture what the moon's length is in a way according or like relative to the earth. Because the umbra is to the earth, right? Anyway, let's go over it. Now, this first part will simply be a recording, right? I'll be telling you records of what has been seen. This is a very, very badly drawn diagram. This is a very, very badly drawn diagram. Yikes. Okay. So now, using records, right, we could see how long it takes for the moon to get past this umbra and how long it takes for it to enter the umbra, right? Now, if we were to take the moon entering the umbra, right, so the time it takes for it to first touch and for it to be fully engulfed, that takes around 1 hour. Okay? And now, the amount of time it takes for it to enter again and for it to have fully left, okay, that takes, at the time, 200 BC, it takes around 2 hours. That is what we have in our record. Okay? So, from this, we get a bit of knowledge. Bit of knowledge. Now we will save this. We'll save this for later. But from this, we could basically say like the radius of the umbra is 2, right? But now there's some more information. This is just a bit of preamble, if you might. From here, we can make a triangle. We can make a triangle. We make a line here to make a triangle, and make a line here to make another triangle. Now here, what is this? This line, the line that we just added. Well, this is obviously the distance to the moon, right? And here, this is just the distance to the sun. All right. Now this line right here, that must be the radius of the Earth minus the radius of the umbra, right? Here's the umbra, right? It's just that. This is the radius of the umbra. So that little line segment must be the radius of the Earth minus the radius of the umbra. Now we know that this is 2 hour, right? We could just say 2 if everything's in terms of hours. But for now, just keep that away. Now this is kind of just the same thing. This is the radius of the sun minus the radius of the Earth. Right? That's what that is. Now these two triangles, if you remember from before, these are similar triangles. If you remember from our previous tablet, right? All of our previous tablets, really. These are similar triangles. Which means the radius of the Earth minus radius of the umbra over the distance to the moon, right? The ratio, this ratio, or this, well, yeah, this ratio, I guess, is the same ratio as the radius of the sun minus the radius of the Earth over the distance to the sun. It's the same, right? The ratio is the same. We know this from law of similar triangles. Now, we also know that this, the distance to the moon, to the sun, this is 20 times bigger. We know that the sun is 20 times bigger. So, what we could do is we just remove these, right? Now we'll have radius of the Earth minus radius of the umbra is equal to 20 times the radius of the sun minus the radius of the Earth. Okay? Because remember, from before, these are similar triangles, so the radius of the moon is also 20 times, and the distance is also 20 times the radius and the distance of the moon, 20 times for the sun. Now we have that, right? Right. Mm-hmm. Sorry, my bad. Sorry, I I misdid it. My bad, folks. It's supposed to be the other. It's the other way around. I'm I'm a fool. Quite frankly, I'm a fool. I believe. Sorry, this is right, but it's it's supposed to be the other way around. Like I could post. Here's the radius of sun minus radius of the Earth is equal to 20 times the radius of the Earth minus the radius of the Earth. Yeah, there you go. Sorry. Yeah, so there you go. And now we know once again radius of the sun is just 20 times radius of the moon, right? And this radius of the Earth. And also we know that the radius of the umbra is just 2 times the radius of the moon, right? Because remember this. Remember this? This just means it's 2 times the radius of the moon. That makes sense? I believe so. Thank you. Right? So once again, let's quickly go through it. So here we have similar triangles, right? The moon, it takes twice the moon's length to go through the radius of the umbra. And we also know that the distance to the distance of the sun, right, is 20 times the distance of the moon, which means we can simplify the ratio of this. And then once again, we know the radius of the umbra is twice the radius of the moon because of just simple analysis of how long it takes to get past, how long it takes for the moon to enter the umbra, and how long it takes for it to get through it. We can just find that. And now, with this, if we simply divide both sides by 20, now we'll have radius of the moon minus 1/20th the radius of the Earth is equal to radius of the Earth minus twice the radius of the moon. And then finally, we just bring these together. So radius of the Earth plus 1/20th radius of the Earth is equal to 3 times the radius of the moon. Now, this 1/20th, we could just say is a rounding error. So, the radius of the Earth is approximately 3 times the radius of the moon. And now it's all coming together. Now we have something that goes. Now we have the Earth. We have the Earth in tandem with the moon. We have a difference there that we could use. This is amazing because now we could change everything to be in terms of the Earth size instead of the moon size. Okay? Now let's try it. Let's try it. So, remember everything is around the size. So I need to get my things. Give me a second. So how can we do this? How can we find in terms of ourselves? Actually, if we go back to the first one, let's go back here. Going back to our beginning. So we know it's 125, right? Remember the number 125? What that represented. Now, for 125, it was the moon is 125 moon length from the Earth, right? Remember, this is 125. This is 125 moon length from the Earth. What about in terms of the Earth length? Well, because we now know that the radius of the Earth is approximately 3 times the radius of the moon, all I have to do is take the 125 and divide it by 3. Now, this gets us to be approximately, we'll say approximately, right? Because it's going to be decimals, and I don't want to do that. I don't want to work that right now. Because decimals don't exist in 200 BC. 42, which means this is around 42 Earth lengths from the Earth. The moon is 42 Earth lengths from the Earth. Right? Now, we could do the same thing with the moon. With the sun. The sun, remember, it's 20 times, right? 20 times the size and the distance of the moon. But also, we have to divide by 3. Same thing. We could simplify this to around 7 times if we want. So let's just do that. I could, what I'll do is I'll put the 20 over 3 here, and I'll say it's approximately 7. And I'll put the 7 here. Remember, if you want, you're always allowed to just yourself do the calculations to see what it actually would be equal to. Now this would be 840. Yikes. Now this means this is 840 Earth lengths from the Earth. The sun is 840 Earth lengths from the Earth. The sun is very, very, very far. It is very far. And it is very big. It is a very, very huge. Now, already here, we have enough information for me to make my conclusion. So, why does this mean that the sun is likely at the center of the universe? Why that instead of the Earth? Well, here is my conclusion. And as a bonus, we will figure out what the actual distances in terms of miles and kilometers are. Don't worry, I haven't forgotten. We're going to figure out what the circumference is and what the radius is and what the distances are. But I want to get this over with. This is the important part. Now we know, right? The sun is huge. It must be much bigger than the Earth, right? Remember, it's around 7 times bigger, right? Around 7 times bigger than the Earth. Now, intuitively, we know that bigger things get revolved around by smaller things, right? Smaller things revolve around bigger things. If you were to take a basketball, right? Take a basketball, or take take a wheel, take a wheelbarrow, right? And then take an apple, right? Take a wheelbarrow, take a wheel, take an apple. Now take a rope. Now the wheel is much larger than the apple. Take a rope and combine them. If you were to kick the wheel, right? What are the chances that the apple would not move and that the wheel would, right? No, the wheel would move because you kicked it. But the apple would also start moving everywhere which way. It would follow the wheel. But now do it the other way, right? If you were now to kick the apple, the wheel wouldn't move unless it was a very small wheel. The apple would go around and around and around that wheel. It's the same thing for the earth and the sun, and even for the moon and the earth. The moon, we now know, is 3 times smaller than the earth. And we already know that the moon revolves around the earth. We already know that. But why shouldn't it be the same thing for the sun, which is so much bigger than the earth? Isn't that right, my disciples? Doesn't that just make sense? To me, it does. So, now that I've come to this conclusion, and to me, it just makes sense. Now we know that the sun must be at the center, and that we must be revolving around it. And that is my proof. And to end this off, let's do something fun. Let us figure out the actual distances and the actual sizes. But to do that, we now have to do something very important. We need to figure out what is the size of the Earth. Very intriguing indeed. I have a way of figuring it out. I do. Now, I had a friend. He was in Cyan. Okay? Now, this friend, he claimed a very interesting fact. And other people said the same thing. He has people to back this up. He said that during high noon on the summer solstice, you could see into the well of Cyan. You could see your reflection. Any other time of the day or any other time of the year, you could not see into that well. That well was like any other well. Right? Now that's awesome. That's amazing. I thought, I need to try this for myself. Because a well is pitch black the entire time of the year, every day of the year. On the high noon of summer solstice, I have to see this. So I went to my well. I went to the well of my city. And I waited until high noon, summer solstice, looked down to the well, and what do you know? Nothing. Pitch black. At first I thought my friend from Cyan was telling lies. I thought the devil had spoken out of his mouth. But then I took a second. I thought, well, hold on. I, myself, am pretty far, right? Now, I live pretty far from Cyan, I must say. I live in Alexandria, or at least at the time I did live in Alexandria. And I thought, well, I know that we are pretty far from Cyan, right? We are we are a few days part away. Perhaps the issue is not that my friend from Cyan was lying. Perhaps the issue is just the distance. This is a realization I came to. Now, let's say here is the Earth. Let me draw bigger. Let's say this is the Earth, and here is the well. Let's say here's the well. Then on high noon of summer solstice, the only way that you could see into the well is if the sun was shooting light, shooting light directly down into that well. Now we know the sun is super far away. We know it's way, way too far away. At this point, we know it's 840 Earth lengths away. And the Earth is huge. Even if we don't know the exact size, we know it is huge. So now, at that point, the rays are all parallel. Or at least as parallel as they can be. Now, maybe my lines aren't parallel, but I think you understand what it is I'm trying to say. Because of how far away I am in Alexandria, I'm around here. Let's say Alexandria is around here, and let's say Cyan is here. Right? It must mean that if I have a well here in the Earth, you see, it's not hitting. I'd have to wait for the Earth to rotate in such a way where it can. So I'm far enough away where the plane is not flat. Because remember, we are on a globe, and we know this. We know this for a fact. We know this for a fact that we are on a globe. So I came to a realization. In Alexandria, we have a large obelisk. We have a large obelisk here. At high noon on the summer solstice, that casts a shadow. Casts a shadow. Now, if only I could get that angle, then I could figure out something very interesting. So, I knew the summer solstice. I went. I went to this obelisk. I took the measurement of the shadow. I took a measurement of the obelisk. Now, this was a triangle, a right triangle. From this, since I knew what the length was of the obelisk and I knew the length of the shadow, I could figure out the angle that caused that shadow, which turned out to be around 7 degrees. It was closer to 7.01 degrees, but we'll just say 7 degrees. Keep it simple. And then I imagined the Earth. I imagined that the well went all the way down into the center of the Earth. And then I imagined the obelisk going down into the center of the Earth. Because they're both flat on the plane of the sphere that is the Earth, they would meet. And then I made a triangle. Out of the shadow. I made a triangle out of the obelisk and the well. And now, here's something. We know that this is 7 degrees because of the measurement that I had made. What this means is that this right here must also be 7 degrees. Why that is because of the law of similar triangles. These must have the same angle because these must be the same triangle, or at least same ratio wise. Okay, you say. Very interesting. Some of you might even know where this is leading. But what does this help us with? We know now that the distance from Cyan to Alexandria is 7 degrees. What this means, right, since we also know that a full circle is 360 degrees, 360, this means that this distance from Cyan to Alexandria is 7 degrees of that. So if we were to divide it by 7, we would get 50. Cyan to Alexandria is 1/50th, right? No, it'd be better to do it the other way. From Cyan to Alexandria is 1/50th the circumference of the Earth. So all we need now is to know how far Cyan is to Alexandria. From that, we could find the circumference of the Earth. And with that, everything will go into place. So, my disciple, at this point, it was obvious what had to be done. So, I got a college student, and for extra credit, I told him to walk it and to get the distance. And he came back, and let me tell you, he got me that distance. Ooh, did he get me that distance? He got the distance to be 500 miles. Approximately 804 kilometers. Now, we could use this information to figure out what the circumference of the Earth is. Ho ho ho. And it is very simple math. Let's take the 500 times it by 50. And we find out that the circumference of the Earth is about 25,000 miles. From this, we could simply use 2 pi r in reverse to figure out what that is for the radius. And we'll be golden. So, 25,000 divided by 2 pi will be equivalent to the radius. Now, this is just about, if I do the math here, it will be just about 3,979. It's closer to 78 point something, but 79 miles. It's not meters. It's miles. I don't really know what the thing is for miles. And now everything will start falling into place. From this, we'll need more space, so I'll do this, and I will say the radius of the Earth is 3,979. We know the radius of the Moon to be, what is it? 3 times. So we just have to take 3,979 divided by 3, and we get another answer. Which is approximately 1,326. And then we know the radius of the Sun is going to be a little bit more complicated. Well, times 7. So, where's the number times 7? 27,853. 27,853. From these, we could find what those are. Duh. And we can now also find the distances. Because what was the distances? That's right. It was wrong thing. Wrong thing. These. Right? In terms of different lengths, we have this. So we could just times them by 125, really. Right? It takes 125 moon lengths. So we could just take the moon length. Or alternatively, we could take the lengths we got from this. But I think it's more interesting to get these. So distance of the moon is going to be easier as well, I think. Just take the distance of the moon, times it by 125. That's our answer. I don't think I'll have enough space, so I will rewrite that. 1326 and 125. You know what? At this point, it's better to just do it down there. Times 125. What's that number? 165,750. That's how many miles it is from the Earth. And the Sun, well, this is going to be a pretty huge number. see what it's gonna be. 300 oh 3,481,625. 3,481,625 miles, 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 and miles. And just like that, we now know approximately, remember these are all approximations, that of the radius of the Earth, the radius of the moon, the radius of the sun, the distance of the moon, and the distance of the sun. And we now know that it is more likely that the Earth revolves around the sun and the sun is in the center than the sun being the thing that revolves around the Earth. There you go. Any questions? Any questions? Probably not. Mm-hmm. Wow. That's kind of it. We've done a lot. We've done a lot today. A lot of math. A lot more than astronomy, I'd say. Remember, disciples, on the disc of Ord tonight, we'll be observing the stars. If that interests you, if you are a stargazer like I, then please feel free to drop on by. I think you will enjoy yourself, as will I. It'll be a great time. A great time indeed. Oof. Kind of surprised I got through all this. I'm not gonna lie. I mean, I did get through it pretty quickly, all things considered. There you go, though. Tonight I'll be going over anything that I might have done wrong, deliberation. I'm pretty good. I want to thank you all, my disciples, for joining me on this day. I'll see you all. Good night. Good night. Good night. Goodbye. Goodbye. Good night. Mwah. I guess people rate out. Usually don't they? I should probably rate out. The question is, does anyone I know is anyone I know live? I don't think so. I think all the people are sleeping. Everyone's sleeping. Sleepy day. There doesn't seem to be any cool science and technology people. I don't think. Seems to mostly be broadcast live seismic event. No weighing. This was fun though. I enjoyed doing this. I'm glad I did. I'm glad I did. Ah. You know what? We're gonna go. This person's doing art. They look cool. Let's rate them. Let's rate them. Once again, disciples, thank you for being here. Glad you could join on in. Uh, remember to stay frosty. uh, eat chicken wings and have fun. Yeah, yeah. Why? Why?